Okay, so how is everyone today? Good? All right. So, just as a point of order, I'd like to point out that this is why I typically have a homework assignment due every lecture. Okay. Good. So let's we'll just move past that. What was I saying? Oh yeah, we've been talking about radicals and fractional exponents and things like that, and now we're going to wrap that up. For now, we'll have plenty more to say about it later, but for now we're going to wrap it up, and then we're going to move to the next bit. Okay. So yeah, I had to think about it for a second. So we've been sort of really heavily using this rule the past couple days. The nth root of a multiplied by b is the nth root of a multiplied by the nth root of b. Now, the reason why that works in the end, and the reason why I claim that this should not be surprising, is that you know, we said last time that nth root means exponent 1 over n. That's its meaning. So that statement is the same as this statement. So then we have a to 1 over n, b to 1 over n, like that. So that's good. And you know, the reason why I claim that that's helpful is that something that we knew before we started talking about radicals and things like that, that we went over very carefully, is we said that if you have xy and you raise that to exponent regular old n, not 1 over n, but n, you know, then we went through the machinery of saying, oh yeah, we're going to write, you know, x, 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 y, 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 and a bunch of x's and y's, and then collect them all out. And we went through that really tedious, you know, so many x's, you know, grids and grids of x's, until, you know, we come to the point, okay, yeah, I think this rule is correct. X to n, y to n. So can you see that, you know, this is the thing that you knew, and in the end, they're all deeply connected. What this is the distribution of exponent over multiply. Okay, good. Now, another thing that we've been using a lot, or that we've used some anyway, is the following: is we said besides exponent distributing over multiply, we can also do it this way. We can say x divided by y, raise that to exponent n. And what do you get? Well, you get this. X to n over y to n. So again, these are basically the same rule, just said in a different way. The reason why these are basically the same rule but said in a different way is that we needed one little piece of machinery that told us that when you write something like y to negative n, that means 1 over y to n. And once you have that, you know, then you have that rule. And now what I'm telling you is that you know, we can walk back out this path going the other way. We can say that all right, suppose I change this to a's and b's and 1 over n's. If I say a over b raised to exponent 1 over n, like that, then what's going to be the result? Yeah, it'll be root like this. It distributes like that. And then we can write that with radicals and say, like this. So you put a fraction inside of a radical, and then the way you can deal with that is you can say, well, I'll just do the radical of the numerator divided by the radical of the denominator, like that. And so what I'm suggesting to you is that I wrote what is, in some sense, really the same rule 6 times. 1, 2, 3, 4, 5, 6 different times. The distribution of exponent over multiply. Okay, but so, you know, let's use it a little bit. So I could ask, well, what's the cube root? How can we simplify the cube root of 16 over 27? The idea being that, you know, we're going to use that. Okay, so cube root of 16 over cube root of 27, good. So we can use that nice rule. And then, you know, this is like 2 problems that we were solving several days ago. So we could say, all right, you know, look, in that view, what we did is factored the stuff inside the radical. So 16, I'll write that as 2 to exponent 4. And then 27, I'll write that as 3 to exponent 3, like that. And now, because, you know, this is now in the format that we were previously dealing with, when we're dealing with cube roots, when you want to simplify, things come out in triplets, right? So if you have any triplets, they can come out as a single one of that thing. So here we have 4 2's. So there's enough to get a triplet of 2's to come out. So a triplet of 2's will come out as absolute value of 2. Well, not even. We wouldn't even need it because 3 is odd. But, you know, absolute value of 2 is 2. So then that 2 would come out. But there'd also be one left because there's 4 of them. So the numerator could be written as 2 cube root of 2, like that. How about the denominator? It'd just be 3, right? Because we've got a triplet of 3's. And so those 3 3's can come out as a single 3. That's kind of an awkward phrase. And there'd be no 3's left in there. So they all come out as just a single 3. There you have it. Any question about that one? Okay. So, you know, I'm not going to take the time to do it, but you know, I'll just mention here we did an example of this when there was just constants, you know, numbers, 16 and 27 and what have you. But we could just as well play this game with variables, right? I could rewrite this exact thing, except in the numerator there, I could write w to exponent 58. And then you'd have to get a bunch of w's to come out. And some would be left. Good. All right, how about here's another kind of thing we can do with radicals. So I could say, again, the request is to simplify. So square root of 72c, and then subtract 2 square root of 2c, like that. All right. So now, you know, the question, a question that is, you know, typically asked, you know, very young kids when they're first, you know, going to school, is you could say something like, well, you know, Susan has 8 apples and she eats 2 apples, then how many apples does she have left? Okay, then, that's a subtraction question. Then you could say something like, to make sure that they really understand it, is you could say, well, Susan has 8 apples and some other fruits. So she's got 8 apples. And then she eats 2 oranges. How many apples does she have left? Still 8, right? And so what that's testing is that, okay, do you understand that we only subtract things that are alike? Okay, now this problem is exactly that, but it's just sort of made in this mathy way. So what I want you to see is that as currently written, these are like 2 different kinds of things. They're like apples and oranges, and the kindness is whatever's in the radical. So notice that for this one, what's in the radical is 72c, and for this one, we've got a number multiplied by this, and what's in there is 2c. And 72c is not the same as 2c. So we can't do anything right now, but if we could come to a place where the thing that's in this radical is the same as the thing that's in that radical, then that would be like a question like about apples. Okay, so then what we want to do is we want to simplify this one, because as for this one, we can't get a 2 out, right? And the c can't come out. There's not we don't have a c and another c. But as for this, maybe this factors and we can get something to come out. So how does 72 factor? Okay, very good. So you could say that as for that 72c, you could say that that's 2 multiplied by 36 multiplied by c, and then subtract 2 multiplied by square root of 2c, like that. And that's this factorization of 72 is probably the best one for this exercise, because, well, that 2 can't come out, right? But how about the 36? Yeah, it can come out, right? And when it comes out of the square root, it comes out as 6. So you could say that this is 6, and then what's left in this radical is 2c, and then subtract 2 multiplied by square root 2c. And now what I want to impress upon you is that as written, this is now an apples to apples question. Because what's important is that what's in the radical is the same. So if I just cover this up and just cover that up, they're the same. So what's being asked is Joey had 6 apples and then ate 2 apples. How many apples are left? 4, right? So can you see it? Looking at the radical thing just might mess with your, until you get really comfortable, it might just mess with your eyes for a second. But it's 6 of these, and then subtract 2 of this same kind of thing. So 4, 2c like that. Good. Any question about it? All right. Good. So another kind of thing that comes up a lot concerning radicals is an exercise like this. So I could say, so the instructions would be rationalize the denominator. So, and a typical prompt would be something like 3 over the square root of 2. Now, to be clear, what's desired, what's being requested, is that we want to have no radicals in the denominator. So I gave you an expression that does have a square root in the denominator, and I'm saying that I want you to respond with something that has the same value, but now there's no square roots down there. Okay, so here's the idea. is that I'm going to take that expression and I'm going to do something, I'm going to do a trick, really. And it's a very common trick. And what I'm going to do is I'm going to multiply it by 1. But now, what I'm going to do is that I just need to be really selective, kind of clever about how I'm going to write 1. So there I wrote 1, and that's not very helpful. So now I need to come up with some better other way to write 1. So I could write 1 as like 5 over 5, say. That's a way to write 1, because if I take this number and multiply it by 5 and then divide it by 5, then I haven't done anything. Same number. But you know, in the end, we want there to be no radicals in the denominator. So here's my trick: is I'm going to say, okay, I'm going to take that number, this number, and note that, you know, if for some reason I could arrange it so that I could multiply that square root of 2 by that square root of 2, then what is the square root of 2 multiplied by the square root of 2? It's just 2, right? So if it was permitted for me to put that there, then that would be okay. But as written, currently, it's this is not correct. Why is it not correct? Right, because if I'm gonna writing that there means that I'm dividing the number by the square root of 2, and that's fine as long as you also follow that up by multiplying that number by the square root of 2. So do you observe that the red bit, that's 1? It's just the most convenient way to write 1 in this case. So then carrying that out, this would be 3 square root 2 over 2. Any question about it? Okay. So now here's another one. So I'll say that that's you know, first example, and then same instructions here. But now I'll give one that's a little more exciting. So how about 5 over 3 plus the square root of 7? All right. So now I'm going to try 3 times to solve this. The first 2 times aren't going to work. All right. So then the reason so the first try that I'm going to do, the reason why I do it is that I find students make this error all the time. So I'm going to do something that is just incorrect. Then the next one is going to be that I didn't do anything that's incorrect, but it's just not going to get me anywhere. So here's the first one. So this is just incorrect. So take the thing, and then you know, I look at that and think, oh, okay, I get it. I just need to do something like that, and then so I'll say that this is 5 over 3 plus the square root of 7, and then I'll say multiplied by the square root of 7 there, and multiplied by the square root of 7 there. But this is incorrect. Now, what's incorrect about it?
You would, in this version, you would need to distribute square root of 7 to the square root of 7, but also to the 3.
Right. Because, you know, to make it right, this has to be 1. You know? And so whatever you're doing to the denominator, you must also do to the numerator. Now, the denominator is all of that. It's 3 plus the square root of 7. Now, as written, did I multiply 3 plus the square root of 7 by the square root of 7? No, I only did just that bit. So you can't just multiply just that bit, right? Just that much. You can't do that. So this is wrong, because to make this right, you know, that would need to be distributed also to there. So this is a distribution error, or if you like, an order of operations error, depending on how you want to look at it. Okay, so that's just not right. So now I'm going to try again, and the thing I'm going to attempt is mathematically correct. So now I'll say, all right, really, I have to put this in parentheses like that. Okay, so now I've done something that's mathematically correct. But now I want you to observe what happens. So then the numerator is as simple as it gets, 5 square root 7. And then when we actually distribute the square root of 7, then what do we have? Right, 3 square root of 7 plus 7. Okay, now, there's nothing mathematically incorrect about what I've written here. Yet, this doesn't satisfy the requirements. Because it says to rationalize the denominator, which means achieve a situation where there's no square root down there. So we haven't made any errors, but we haven't made any progress either. All right, so then fine. So we need another idea. So it's not enough just to know the multiply by 1 idea. You need, to solve this exercise, you need one more thing. So we need the idea, and the name for it is conjugate. Now, to understand the word conjugate, in physical science and things like that, two items are said to be conjugate if they fit together, and when fitted together, somehow a mechanism works. So a typical example would be something like a lock and a key. So, you know, ignoring issues of like breaking and entering and blowtorches and what have you. Okay, ignoring that. You know, you've got a lock and you've got a key, and separately they don't operate when they're separated. But when they're fitted together, then the mechanism works. Another example would be like in chemistry. Some chemical reactions proceed very slowly. And then, you know, one of the neat things is that for some chemical reactions, you can introduce another item in there that's not actually consumed by the reaction, but its presence causes the reaction to speed up, usually dramatically. So what's the name of such things?
Catalyst.
A catalyst, right? And then, you know, human beings are really just walking, and all creatures for that matter, are just like walking chemistry experiments going on. You know, literally, even now, millions, tens of millions of chemical reactions are happening all the time in every one of us. And they're happening extremely quickly because they're in the presence of catalysts. But, you know, biology is special, and biologically manufactured and situated catalysts have their own special name. What's their name? Which one? Enzymes. Okay, so, you know, in a biological situation, catalysts are referred to as enzymes. So one of the main things that your body is doing all the time is manufacturing enzymes. And the way it works, actually, is that if you have a chemical reaction with 2 or more components, I'll just say 2, then the way an enzyme works is it's a big, protein that's got a nice geometry to it. And what happens is that chemical A sits just perfectly in that spot, and chemical B fits just perfectly in this other spot. And when those spots are filled in the catalyst is said to be conjugated, because it's all the stuff is fit together. And the way the enzymes work is very, very, very quickly. You know, it's like holding, you know, chemical A here and chemical B here, and then very quickly it sort of does a twist and pushes them together, and that causes the chemical reaction to proceed immediately. And as soon as that proceeds, the enzyme lets go, and it's ready to do it again. It's not used up. It's a beautiful thing. Conjugate. Now, in a math context, it's a little bit more abstract. But here it is that the binomials a plus b and a minus b are conjugates, or they are called conjugates. Now, because it's math, and math is, kind of an abstract thing, I can't explain exactly all the reasons why we want to call these two things conjugate to each other, but I can give you a pretty good glimpse of it right here because it's what we need. And, all right, I'll observe the following, that we have a plus b, and if we take that and then multiply it by a minus b, then, that's a binomial, and these are conjugates of each other. So this is the product of two binomials, and we've got a nice formula for the product of binomials. What is, and it even has a cute name. What's its name? Starts with F. FOIL. Okay, so then, we just write it out. There's 4 terms. What's the F term? Well, yes, I agree. But I mean, like, for this specific case? A squared. And then the O? Minus AB. The I term? Okay. And I agree that it's BA, but I'm going to write AB because multiplication commutes. And then the L term? Minus B squared. Now, what I'd like for you to observe is that in FOIL, there's these 4 terms. And the F and the L term, they're called pure in the sense that this one only has A and this one only B. And the ones in the middle are called mixed in the sense that they have A's and B's. And do you observe that as for the mixed terms, when you simplify, they're gone. They cancel each other. So A squared minus B squared. That's interesting. So anytime you multiply 2 conjugates, there are no mixed terms. They poof, they vanish. So with this context, I can say, all right, here's my 3rd attempt. We're going to get it this time. 5 over 3 plus square root 7. We are going to multiply by 1. That's going to have to happen. But, I suspect that I probably made it overbearingly obvious what we're going to multiply by. So what are we going to multiply by?
3 minus the square root of 7.
There you go. So that's what we need down there, the conjugate of that. But we can't just put that just there, right? It needs to go up here too. Minus. Oops, that's a minus. Okay. So that's a minus. Sorry about that. I was writing in pen and I can't fix it. Okay, so then the numerator would be 15 and then minus 5 square root 7. And then this, you could do FOIL if you like, or you can remember this. This is the product of conjugates. So it's going to be the first thing squared, and then minus the second thing squared. So it's going to be 3 squared, and then minus square root 7 squared. All right, well, 3 squared is 9, and square root of 7 squared is 7. So this is 15 minus 5 square root 7 over 9 minus 7. So 15 minus 5 square root 7 over 2. So do you observe that, at any rate, there's no more square roots down there? it's not exactly clear to me. You know, I've taught this course a lot, and I have no idea why every college algebra book is so interested in achieving this trick. You know, if you didn't want any radicals down there, then why'd you give me a question with one down there? I don't know. I don't get it, but fine. Now, the reason why this mechanism works anyhow is that notice that, you know, so on the first time, that's just a math error. That's just wrong. For this one, there's no math error, but the problem is that we still had that. That's a mixed term. That's what that is. We had one of that kind and one of that kind, and they were mixed. The point of using the conjugate trick is that when you do it, notice that the mixed terms cancel. No square roots. Any question about it? Okay. Fine. So next, and now we can talk about new stuff. Right. So now we're going to define something called a polynomial term. So polynomial term. Okay. So here's the setup. Let A be in the reals with A not 0. So what I'm saying is that, you know, pick your favorite real number that isn't 0. Okay, so there you go. And now say blah blah, and then now I want to in the naturals like that, and x is a real variable. So what I'm saying is that the difference in the language is that you go ahead and pick your A, whichever A that you like, but besides 0. And then x is going to sort of be able to be anything at all. But your A is fixed. Okay, so then with these three symbols, we have the following cases. So I've got two different things to do, so I'll write a little bit on the left side, a little bit on the right. So the first case we need to deal with is the case when n is 0. So it's fine for n to be 0, but, you know, A can't be 0. Could you remind me, what's the definition of the naturals? Non-negative integers, right? So 0, 1, 2, 3, 4, but not 2.3, that's not all right. And not -5, that's not all right. So in the case that n is 0, just the single expression A, whatever your favorite number is. So if you said, I'm thinking of my favorite number, and you said 7, 7. This is called a constant. Degree 0. Polynomial term. You know, and it as an example could be just be something like just a 7. In the case that n is greater than 0, in that case, we're talking about something like this. So A multiplied by x to exponent n, like that. So in this case, it's called a non-constant. Non-constant. Degree n. Coefficient a polynomial term. Okay, and an example could be something like, 3 times x to 2, something like that. So now, the reason for the language constant is that concerning this polynomial term, I could say, well, what's its value when x is 1? Which is to say, plug in x is 1, and then tell me what you get. Well, you get 3. And if you plug in x is 2, well, that'd be 2 squared. That'd be a 4 times 3. That'd be 12. If you plug in 2, you get 12. And if you plug in other numbers, you get other things. But as for this one, what do you get when you plug in x is 1? You get 7, right? What do you get when you plug in x is 2? 7, right? And then asking this in sort of a more human way, I could say, what's the value of 7 on a Wednesday? 7, right? 7 doesn't really care what day it is. That, 7's a constant. It doesn't do anything. But this one, this one depends on x. Whatever the value of this is, it depends on what you plug in for x. But that one, it doesn't. So this is a constant term, and this is a non-constant term. All right. So let's see some examples of various things that might or might not be polynomial terms. How about 23 times x to 10 there? So is it or is it not a polynomial term? So, and if it isn't, then why not? If it is, then what's its coefficient and its degree? No, so that won't be given. So x is just like a place where you're going to put something in.
Oh, okay.
So is it a polynomial term?
It is.
It is. It has degree what? 10. And coefficient what? 23. All right. What about say 3/2 x squared? Is that a polynomial term? It is?
Oh, no, never.
What's not?
That doesn't have to be natural.
I agree entirely that 3/2 is not natural. But I also agree that that actually doesn't matter. So why does it not matter?
Because it's still real.
Because, right? Remember the coefficient, the thing that's in front, that can be any real, right? It's the exponent that we're saying we've got to have a natural exponent. Okay, so this is fine. So degree degree 2, coefficient 3/2. Okay, fine. Then what about this one? What about 5 multiplied by x to 7/3? What about that one? Yeah, this is not a polynomial term. Why not? Right. Because that 7/3 is not natural. Oh, a witch? Is that what I heard? Yeah. Not natural, therefore, now I'm all off track here. No, therefore, not a polynomial term. Okay. What about how about this 5, another 5. So 5 square root of x. Is that a polynomial term? No? So if no, then why no?
Because the square root of x is equal to x to the 1/2 power.
All right. So then I agree. So radicals can be understood as fractional exponents. So writing it in that way, that means this. 5 multiplied by x to half. And now the question is, well, is half a natural or is it not? It is not. So half is not natural, and therefore this is not a polynomial term. All right. And then immediately below this one I'm going to write, what about this one? The square root of 5 multiplied by x. Can't really fit the whole page up there. How about that one? Is that a polynomial term? So now I've got you shy about the radicals, right? I primed the question with that one. So just like this one, you know, the question, the way that the question is clearly answered is you say, well, in some sense, I need to know what the exponent for x is, because you gave me an expression, but it wasn't explicitly written down as half. I had to remember that it was half. Now, I didn't write any exponent for x yet, because of the rules that you know. You need to be able to tell me what is x's exponent. It's 1, right? So writing that down and having a look at it, then, you know, we need in a sense two things for this to be a polynomial term. We need something to be true about the coefficient, and we need something to be true about the exponent. So does it satisfy those things? Yeah, right? Square root of 5 is just some number. I don't know what it is off the top of my head. It's got to be something like, you know, more than 2, but less than 3. It's some number. And then the exponent is 1. Is 1 natural? It is. So you can say that this is degree 1 and coefficient square root 5. Okay, and then for completeness, how about this one? 2 multiplied by x to negative 4. How about that? Is that a polynomial term? It is not, because negative 4 is not natural. So therefore, not a polynomial term. So any question about these? So now that I've told you what an individual polynomial term is, now I can tell you what a polynomial is. So a polynomial, and I'll just write that as poly, a polynomial is a sum of polynomial terms. So, you know, now I could do another entire sequence of exercises where instead of writing just one term and asking you, is it a polynomial term? Now I can write an expression that's got like 2 or 3 or 4 terms or whatever in it and say, is this a polynomial? Now the question is, that means, is it the case that every one of those things that I wrote down is a polynomial term? So if that's the case, then it's a polynomial. And to make sort of a physical analogy, it could be like if you go to the grocery store into the produce section and you're looking around, then you're either looking at a bag of oranges or you aren't. So if you're looking at a bag of oranges and then I put a potato in there, is it a bag of oranges anymore? It's not, right? Because to be a bag of oranges, you need everything in there to be an orange. Okay, the same kind of way that to have a polynomial, every term has to be a polynomial term. All right, the standard form of a polynomial is like this. So, all right, so we could have just a0. So I'll explain what I mean by that in just a second. So we could have just a0, or we could have something like a1 multiplied by x plus a0. Or we could have a2 multiplied by x squared plus a1 multiplied by x plus a0. Now, in this case, we'd need a0 to be not 0, and in this case, we need a1 to be not 0, and we'd need, in this case, a2 to be not 0. So what I want you to see is that the pattern is going to be, now I didn't write an exponent for that x, but what's its exponent? 1. So all I mean by a1 is I'm just saying that I'm going to name all the coefficients a, but so that we have a different name for each one of them. I'll say this one is named a0, that one's named a1, that one's named a2. So generally it looks like this. So dot 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 dot. A n multiplied by x2n plus dot 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 plus a2 x squared plus a1 x plus a0, and we need the coefficient all the way over there to be not 0. So now that's the sum of several polynomial terms. And so such a thing is called a polynomial. Now each one of the terms has a degree. So, for example, the degree of that term is 2. And the one next to it that I elided out and didn't write, it would be degree 3 all the way down the line. And then this one is degree n. So the degree of the whole polynomial altogether, taken as a bag of polynomial terms, it's the degree of it's the greatest of all degrees. So this polynomial is said to be degree n. This one is degree 2. That one is degree 1. That one is degree 0. Now, generally, we're also going to be interested in the numbers, all the ANs and things like that. So for this one, it's a leading coefficient. Leading coefficient is called AN. Is that one. It's the coefficient of the term which has highest degree. And then we also have the constant coefficient. And that's a0. It's that number. It's the only one that's constant, the thing that doesn't have any x's. So leading coefficient, constant coefficient, and degree. So now, here's the deal about a polynomial. Is that, I could give you an example. So something like, suppose that we have 1 x cubed plus 3x squared plus 1x plus 4. Now, under normal circumstances, you won't write the 1. You'll just write x cubed. But then the 1, 3, 1, 4 joke wouldn't be so clear. Now, the thing is that if I wanted you to plug in some x, like if I said plug in x is 10, then, you you could do 10 times 10 times 10 times 1. Okay, and then write that down. And then you could do 10 times 10 times 3 and write that down. And then, you could do it. And to carry out that whole calculation, even if I were to change one of these pluses to a minus, there'd be just 3 operations that are necessary. Multiply, add, and subtract. And no divides, right, in particular. So polynomials are really nice in the sense that to plug in an x, to plug in a value, you only need add, subtract, and multiply. And mathematicians and science, we just love polynomials. So everything that you ever did with integers in grade school, Miss Harris's class and things like that, we're going to do with polynomials. We're going to want to add them. We're going to want to subtract them. We're going to multiply them. In fact, we've already been doing that a little bit in some of our assignments, because this information, according to the state of Texas, is we're still reviewing stuff that you already knew before you got here. Fine. But here's an interesting thing. You remember in Miss Harris's class when, like when you're like 7 or whatever, and she said, okay, class, everybody has 23 M&Ms in front of them, and now we're going to do a math exercise, and if you do it right, you get to eat some M&Ms. And that's how you really, really get the attention of a 7-year-old, right? Everybody's a scientist now. And you say, okay, I want you to make groups of size 4. And then everybody who does it right gets to eat some of the M&Ms. And then every single student has quickly and efficiently found that there are 5 groups of size 4 and there are 3 left over. You remember that? And then you get to eat the 3. So that's the house thingy. You remember doing division where you have a house and then you got to do the whole thing? We're going to do that with polynomials too. And there's going to be quotients and remainders. It's going to be glorious. But that's all that we have for today. So I hope you have a wonderful Friday.